Welcome to AP Podcast 6.4. This is on the standard enthalpy of formation. Now, when you think about what we've done so far, if we want to find the heat involved in a reaction, or the heat transferred between a metal and something, we can use a calorimeter to measure that. And in the last section, we used Hess's law to look at different reactions and manipulate them to get the energy. Sometimes it's impractical to use a calorimeter. Sometimes you just want to find out how much energy is involved. And you can do that with what is known as the standard enthalpy of formation. And it's simply just the energy that changes when 1 mole of the substance is formed from its elements. And there's a chart in the back of the book that's very useful, but it's going to help us do some problems that would be a little impractical for using a calorimeter to find the energy change. So a couple of things we need to do. We need to kind of define where we're at. And to start with that, we've got to know what the standard states are. So because all the energy of the enthalpy of formation is always going to be done with the standard states. And so what is that? Well, for a compound, there's a couple things. If it's a gas, it's the pressure at 1 atmosphere, and you're kind of used to that from other things. If it's a solution, it's exactly 1 molar. Now, we haven't really gone over molarity too much, but that just means there's 1 mole in 1 liter. And then if it's a pure substance, let's say salt or sugar or water, it's whatever the substance is at that point. Okay? And then the other option it could be, you could have an element. And the element is whatever its standard state would be at 1 atmosphere, which again is like room, what we deal with every day, and then 25 degrees Celsius, which is a little bit warmer than room temperature. So you can kind of think of these things as where would you find them just in an everyday setting. So that would be their standard state. So if we think about how to form a compound from its elements at standard state, let's look at an example. All right, so we're going to find the enthalpy of formation for this molecule right here, which happens to be ethanol. And ethanol, it turns out when it forms, it gives off 279 kilojoules per mole. All right, and if you can see the reaction below here, we've got 2 carbons combined with 3 hydrogen to give you 1/2 of an oxygen. Now what you notice here is important is we're making 1 mole of the stuff. All right, and that's kind of the definition is what is it, how much energy is involved in making 1 mole of stuff. So in other words, there's got to be a coefficient right here of 1, or in most cases we don't write a 1 there. Okay, so if you do this reaction, you get 279 kilojoules per mole of methanol. And that's from the element carbon, it's a standard state, the element hydrogen at its standard state, and the element oxygen at its standard state. So there you go. That's the enthalpy of formation. And it turns out that we can look at a table and figure out exactly what that would be. So before we do that, though, let's look at making sure we can write out the reaction. So when you write it out, you've got to make sure that whatever compound you're forming, in this case, we're going to be forming NO2, nitrogen dioxide. And what is nitrogen dioxide made of? Well, it's made up of 1 oxygen atom and 1 mole of oxygen and 1/2 mole of nitrogen gas. And again, you've got to make 1 mole of the substance. So let's try it. Or actually, try this. Pause the video, see if you can do that for methanol. And I'll give you a hint. It's very similar to the ethanol one we did before. So pause the video and do that. Okay, how'd you do? This is the way it would work. Carbon in its standard state. What's carbon basically at room temperature? It's a solid. Okay. Then there would be some. Let's do hydrogen. And how many hydrogen do we have? We have 4 hydrogen atoms. So for us, that would be 2 H2. As you guys know, hydrogen floats around in pairs. And what's the standard state of hydrogen? It's a gas. Plus oxygen. Now there's only 1 oxygen atom. We know that oxygen floats around as O2 in the gaseous state, right? So what do I have to do here to get 1 of those, or 1 mole of those, I should say? I need 1/2 mole of that. Okay? And so here is the standard states of formation for methanol, CH3OH. So there you go. Hopefully that's what you did. I don't know why this little keyboard keeps popping up. All right. So there you go. And we'll practice a couple of these, but for the most part, they're pretty straightforward. Okay. So on to the next thing. Now, I mentioned that there's a table in the back that gives you some energies. I just wrote up a little bit of this. If you go to page A21 in the back of your book, and if you have your textbook with you, you really should do that because you're going to need it to do the problem, or at least confirm that my numbers are right. But if you go back there, you'll see a table, and it's got all these things. Right now, for us, we're only concerned with this delta H. Okay, we will do delta G and S in the next chapter, but right now we're just worried about this delta H. Okay, so here's the heat of formation of aluminum. Well, how much energy does it take to form aluminum? Well, it doesn't take any because it's an element, right? How much energy does it take to form aluminum oxide from its basic elements? Well, it turns out it takes 1,676 kilojoules per mole. All right, and so there's all the common compounds that we use. It's right there, and it's a table that you're going to refer to quite a bit here in the next few days. Okay, all right. So let's look at what we can do with this information. Since we can manipulate the equations, we can use those heats of formation to figure out exactly how much heat would be used in a reaction. And again, like I said, if we wanted to experimentally do this, we could, but sometimes it's not very practical to do it with with a calorimeter. Like for example, right here. This is methanol again, and if we wanted to burn methanol and get CO2 and water, it would be very challenging for us, at least in our high school chem lab, to figure out a way to calculate the energy involved. We could burn it and have the heat go into a can, and that can would heat water. We could figure out, but we'd be losing a lot, or a lot of the value. We'd have a pretty high percentage error. So what we could do is we could go back to the page A21 in our appendix, and we could get the values for the heat of formation of methanol and oxygen and carbon dioxide and water and figure it out. And what we're going to do is we're going to use this very, very helpful formula, which is just the heat of the reaction, okay, is going to equal the sum. Those of you guys in calculus and all that know that. The sum of the heat of the reaction of the products minus the sum of the heat of reaction of the reactants. Okay? And what's important is, just like when we were doing Hess's law, if we've got a coefficient there, we've got to multiply that value by that coefficient. Super important thing. So I'm just going to write down the numbers as if I have the table in front of me, which I do. If you have your book in front of you, you should look and make sure I have the right number. So here we go. So it's the sum of the products minus the sum of the reactants. So what I'm going to do right now is I'm going to go 2 times, okay, and I'm going to find the value for CO2. And the value for CO2 is a negative 394 kilojoules. Okay. Now it's kilojoules per mole, but I'm going to leave off the mole part if you don't mind. If you think about mole here, written mole there, it all cancels out and it works out just fine. So that plus 4 heats of formation of water, so 4 times a negative 286 kilojoules. Okay. Now remember, it's the sum of those. So all that added together minus the sum of the reactants. Okay. So minus, and then I find methanol there. And let me, sorry, I'm just taking my time looking for my chart here. Methanol happens to be 2 times a negative 1454 kilojoules. Okay. Oh, geez, that's horrible. I'll tell you, this darn pen. I mean, you guys know I don't have great penmanship, but this tablet I'm using this year is just horrible. Okay. plus whatever oxygen is, right? But what about oxygen? If you look at the table, you'll notice that the heat of formation for an element is 0. Okay, so that value is 0. So when I do all my little math and I calculate it out, and that equals... Oh, you know what? I'm sorry. I made a mistake here. I've got to... Some of you are probably screaming at the screen going, where am I getting this number? Alright. How about this? A negative 239 kilojoules. And when you add all that up together, you get a negative 1454 kilojoules. Okay? So that's how much energy we get when we burn 2 moles of methanol. Now, one little glitch I want you to be aware of is sometimes you'll get a question like this, but they'll want to know how much energy for 1 mole. Okay? I can't tell you how many times I see that on test questions, AP questions, and you've got to pay attention to the coefficient. Because we're going to work this out, and students will get this all worked out, and they're all happy, and they got the answer, and they write it down, and they forget that, wait a minute, they're asking for 1 mole. So you've really got to pay attention to the question. Now, if they just want to know the heat of reaction for that reaction, no problem. But every once in a while, they'll ask for the heat of reaction for 1 mole of a substance. So something to be aware of, all right? So we'll practice some of those problems, and hopefully it's not too bad. And like always, if you have questions, we'll talk about it tomorrow. Have a great day. See you next time.